Imagine standing on the moon. There is no wind, no sound, no ocean, no trees moving in the distance, only a black sky, a brilliant sun, and beneath your feet, a world that looks completely silent. From far away, the moon seems almost simple, a sphere of gray rock, covered in craters, orbiting Earth. We have photographed it thousands of times. We have walked across it. We have drilled into its surface. We have brought pieces of it back to Earth. And yet, the moment you begin asking what is actually beneath that surface, the moon becomes much stranger. Because the ground beneath an astronaut's boots is not the whole moon. It is only the thinnest visible layer of a world that extends hundreds, then thousands of kilometers downward. And somewhere beneath those familiar gray plains are layers of rock that have not seen sunlight for billions of years. There may be ice trapped in places where the sun never rises. There are ancient materials preserved inside craters. There is a mantle that once moved on a planetary scale. There is a metallic core. There are seismic waves traveling through the interior. And there are clues that the moon may have undergone a dramatic transformation early in its history, when its interior was hot enough for enormous amounts of rock to melt. But perhaps the strangest part is this: we have never actually seen most of the moon, not directly. Everything below the surface has to be reconstructed from clues. A spacecraft measures the gravity. A laser measures tiny changes in the shape of the moon. A seismometer records vibrations traveling through the ground. A spectrometer detects chemicals from orbit. An astronaut collects a rock. And scientists put all those fragments together. It is almost like trying to understand the inside of a human body without ever opening it. You cannot simply look. You have to listen. You have to measure. You have to infer. And that means the moon hiding beneath us is not a science fiction mystery. It is a scientific one. The first layer is surprisingly familiar. If you could somehow remove the top layer of lunar dust and look downward, you would encounter what scientists call regolith. It is not ordinary soil. There is no biological material creating rich, Earth-like soil. Instead, the lunar surface has been slowly pulverized by billions of years of impacts. Tiny meteorites, large asteroids, microscopic particles traveling through space. Every impact breaks rock apart. The fragments hit other fragments. Those pieces break again. Over enormous stretches of time, the upper surface becomes a mixture of dust, crushed rock, glassy particles, and fragments of ancient material. Some of the glass itself was created by impacts melting rock for a brief instant before it cooled. The moon has been continuously bombarded for almost its entire existence, and, unlike Earth, it has almost no atmosphere to protect it. On Earth, a small piece of space debris may burn up before reaching the ground. On the moon, there is almost nothing standing between the incoming object and the surface. So the surface is constantly being altered. But there's another difference. On Earth, weather slowly erases the evidence. Rain, wind, rivers, oceans, ice, plants, plate tectonics. The surface of Earth is constantly being recycled. The moon has almost none of that. There is no rain washing a crater away, no river carrying lunar soil into an ocean, no atmosphere creating familiar erosion, no global system of plate tectonics constantly rebuilding the surface. So an impact that happened billions of years ago can still be visible today. The moon is, in a sense, an archive, a damaged archive, a dusty archive, but an archive nonetheless. And that is extremely important, because when scientists study the moon's surface, they are not simply studying the moon. They are studying pieces of the early solar system. Some of the oldest rocks ever examined by humans came from the moon. The Apollo astronauts collected samples from several different lunar regions, and those samples transformed our understanding of the moon's history. But even those rocks tell us only so much, because a rock collected from the surface is like finding one brick on the outside of a building and trying to determine the entire architecture beneath it. To go deeper, scientists needed another method. They needed to make the moon reveal its interior without digging thousands of kilometers into it. The solution came from something that seems almost ordinary: vibrations. When something shakes the ground, the disturbance travels through it. You experience this on Earth when an earthquake sends waves through the planet. Some waves travel through solid material, some can travel through liquids, some move along the surface, and each type behaves differently depending on what it encounters. Rock, metal, liquid, dense material, less dense material, a boundary between layers. The waves change. They speed up, they slow down, they bend, they reflect, they disappear. And by studying those changes, scientists can reconstruct what lies beneath. The moon has its own earthquakes. We call them moonquakes. Some are caused by the moon's interior cooling and contracting. Some are caused by tidal forces from Earth. Some are associated with meteorite impacts, and some are surprisingly deep. During the Apollo missions, astronauts placed seismometers on the lunar surface. These instruments listened to the moon, not metaphorically, literally. They recorded vibrations traveling through the lunar interior. For years, scientists have used those measurements to build models of the moon's internal structure, and the picture that emerged was far more complicated than a simple ball of rock. Beneath the crust is the mantle, and beneath the mantle is the core. But those words can make the moon sound more settled than it actually is, because the exact structure of those layers is still being investigated. Even today, scientists debate details about the moon's deep interior. How large is the core? How much of it is liquid? Does it contain a solid inner core? What elements are present? How did the mantle evolve? How much did material move inside it? And perhaps most importantly, what happened to the moon's interior as it cooled? To understand that mystery, we have to go backward, much farther backward, before there were craters, before the moon had the face we see today, back to the beginning. The moon is about 4.5 billion years old. That number is almost impossible to visualize. If the entire history of Earth and Moon were compressed into a single day, almost everything humans have ever done would occur in the final tiny fraction of a second. The moon formed when the solar system itself was young. But how? The leading explanation is spectacular. Early Earth was not the quiet blue planet we know today. It was surrounded by debris. The young solar system was violent. Planets were still growing. Large bodies collided. Orbits shifted. Material was thrown into space. And one enormous collision involving the young Earth is thought to have produced the material that eventually became the moon. The details of that event remain an active area of research. The basic idea is called the giant impact hypothesis. A giant impactor, a Mars-sized body, often called Theia in popular descriptions, struck the young Earth. The collision was enormous. Material from the Earth and the impactor was thrown into orbit. That debris eventually gathered together under gravity, piece by piece, rock against rock, fragment against fragment, until a new world emerged: the moon. But there is a fascinating clue hidden in the chemistry. Earth and Moon are remarkably similar in their isotopic compositions. That similarity became one of the reasons scientists became interested in models in which the moon formed from material closely connected to the early Earth. Yet the story does not end with the moon assembling itself, because after the collision, the young moon was nothing like the cold gray sphere we see tonight. It was hot. Very hot. So hot that large portions of its outer layers may have existed as molten rock. Scientists refer to this early molten state as a lunar magma ocean. Imagine looking at the moon billions of years ago. There would be no familiar gray surface, no peaceful craters, No astronauts. Instead, enormous regions of molten rock would glow beneath the darkness of space. The young moon was a world undergoing separation, and gravity was about to perform a remarkable act of sorting. Different minerals crystallize at different temperatures. As the magma ocean cooled, minerals began to solidify. Some were dense, some were relatively light, some sank, others floated. A famous example is anorthosite, a rock associated with the lunar highlands. The moon's early crust is thought to have been dominated by minerals that could float above the denser molten material beneath them. In a way, the first lunar crust may have formed like a frozen layer floating on an enormous ocean of magma. But then, something even stranger happened. The interior did not simply freeze into a perfectly layered sphere. The chemistry of the crystallizing minerals caused the remaining molten material to evolve. Some dense minerals eventually formed at depth. Some of those materials were unstable in their position, and this could have triggered a process known as mantle overturn. Imagine a pot of material in which the denser material ends up above lighter material. That arrangement is gravitationally unstable. The denser material wants to sink. The lighter material wants to rise. On a planetary scale, that can produce enormous internal movement. The moon may have experienced something like this early in its history. This is not merely a dramatic idea invented for storytelling. Geophysical models and lunar observations provide evidence supporting a complicated history of mantle evolution. A 2023 study in Nature combined geophysical and genetic constraints with thermodynamic modeling and reported strong evidence consistent with a lunar solid inner core and a mantle overturn scenario, while noting that earlier seismic observations did not resolve the inner core directly. And this gives us our first glimpse of the deeper mystery. The moon may look dead, but its interior carries the memory of a violent beginning. Its rocks remember an ancient ocean of magma. Its chemistry remembers minerals separating under gravity. Its mantle may remember enormous movements that happened billions of years ago. And its core may still preserve information about how the moon once generated a magnetic field. But before we travel all the way down to that core, there is another mystery much closer to the surface. Something that should not be there. Something familiar to every person on Earth. Water. For much of modern lunar exploration, scientists thought the moon was essentially dry. The early Apollo samples seem to support that picture. The lunar surface looked brutally hostile to water. There is virtually no atmosphere. Temperatures swing dramatically. Sunlight can heat exposed surfaces intensely, and liquid water cannot simply sit on the surface under lunar conditions. So, for decades, the mental image was simple. The moon was dry, dead, desiccated. Then, the evidence began to change. Spacecraft detected signatures associated with hydrogen near the lunar poles. Radar observations revealed unusual properties inside permanently shadowed craters. And in 2009, NASA's L-Cross mission deliberately crashed into a permanently shadowed crater near the lunar South Pole. The spacecraft was not destroyed by accident. The experiment was the impact. A spent rocket stage slammed into the crater, throwing material upward. A following spacecraft passed through the plume and analyzed what had been excavated from beneath the surface. The result changed the lunar story. Water ice was detected in the material thrown out by the impact. NASA later described the evidence as confirming water in the form of ice crystals in some places. But now the moon became stranger, because the important question was no longer simply, is there water? It became, how did it get there? And then an even more interesting question appeared. Where exactly is it? Because the moon's poles contain places that sunlight essentially never reaches. The reason is the moon's extremely small axial tilt. Earth is tilted by about 23.5 degrees. The moon's tilt is only about 1.5 degrees. Near the lunar poles, the sun therefore stays extremely close to the horizon. A mountain can cast an enormous shadow. A deep crater can hide its floor from direct sunlight. And in some locations, sunlight never reaches the bottom. These are called permanently shadowed regions. NASA describes some of these places as among the coldest environments in the solar system. The temperatures can become low enough for volatile substances, including water, to remain trapped rather than escaping into space. Think about what that means. Somewhere on the moon, there are places where sunlight has not directly touched the ground for billions of years. Not a long winter, not a long night. Something far more extreme. A geological refrigerator, a natural cold trap. And inside these dark regions may be materials that arrived long ago and became preserved. Water, volatile compounds, ancient chemical traces, perhaps even a record of how the lunar environment changed over enormous periods of time. But there is an important correction to the popular image. The moon is not hiding underground oceans. We should not imagine enormous lakes beneath the surface. The evidence points to water primarily as ice and other forms of hydration, especially in extremely cold regions, with its distribution and physical forms still being studied. NASA's current lunar science overview notes evidence for ancient ice in permanently shadowed craters, as well as H2O molecules on sunlit parts of the lunar surface. And in 2024, NASA reported an analysis indicating that evidence for lunar ice deposits may be more widespread within permanently shadowed regions than previously recognized, extending beyond the immediate South Polar region. But now the mystery becomes deeper. Because if water can survive on the moon, perhaps the moon is not simply a place where material disappears. Perhaps it is a place where material becomes trapped. And that changes the meaning of the word beneath. Beneath the bright surface may be layers of material protected from sunlight. Beneath the dust may be ice. Beneath the craters may be ancient deposits. And beneath all of that, there is an entire planetary interior. So the moon has two very different kinds of hidden worlds. One is created by darkness at the surface. The other is created by depth. And they tell us completely different stories. The dark polar craters preserve things from outside the moon. The deep interior preserves things from inside it. One may tell us where lunar water came from. The other may tell us how the moon itself was born. And if we want to understand what is really hiding beneath the moon, we have to descend. Not a few meters, not a few kilometers, thousands of kilometers, through the crust, into the mantle, toward the core. And the deeper we go, the less certain the picture becomes. The lunar crust itself is not uniform. That may sound like an ordinary geological fact, but the moon has a remarkable asymmetry. Look at the side facing Earth. It is dominated by broad, dark regions known as maria. The word comes from Latin for seas. Ancient astronomers thought these dark areas might actually be oceans. They were not. They are vast plains of basaltic rock created by ancient volcanic eruptions. Now turn around. Look at the far side. The landscape changes dramatically. The far side is much more heavily covered with craters and has far fewer of these enormous dark basaltic plains. For centuries, humans could not even see the far side. The moon rotates once on its axis in almost exactly the same amount of time that it takes to orbit Earth. That is why the same hemisphere generally faces us. This is called synchronous rotation, or tidal locking. So when you look at the moon from Earth, you are always looking at roughly the same side. The far side was hidden until spacecraft finally traveled around the moon. And when they did, scientists found something unexpected. The moon was not symmetrical. The near side and far side had developed differently. The crust on the far side is generally thicker. The near side contains large volcanic plains. The distribution of certain elements differs between the two hemispheres. Even the concentration of heat-producing radioactive elements appears to have been different. Something happened to the moon that made one hemisphere fundamentally different from the other. But what? That question leads us back underground, because the difference may have begun when the moon was still young and partially molten. Imagine the lunar magma ocean slowly cooling. The first minerals begin to crystallize. A crust develops. The remaining liquid becomes chemically different from the original magma. Some elements become concentrated in the residual melt. Among them are elements that produce heat through radioactive decay: potassium, thorium, uranium. These elements are not magical sources of endless heat. They decay naturally. And as they decay, they release energy. Inside a planet, radioactive decay can contribute to the long-term thermal history. The moon is much smaller than Earth, so it cooled more rapidly. But it did not cool uniformly. Its near side and far side may have evolved differently. The near side became the location of extensive basaltic volcanism. The far side retained more of its ancient crust. And that means that when we look at the moon from Earth, we are not merely seeing one face of a sphere. We are seeing one chapter of a much larger geological story. The dark maria are scars of ancient interior heat. They are places where molten rock once reached the surface. Some of those volcanic eruptions happened more than 3 billion years ago. And surprisingly, lunar volcanism may have continued much later than scientists once thought. NASA's Lunar Reconnaissance Orbiter has identified small volcanic deposits that suggest the moon may have experienced volcanic activity as recently as roughly 50 million years ago in some locations. That sounds ancient to us, but compared with the moon's age, it is remarkably recent. Imagine a world that formed billions of years ago and still had volcanic activity tens of millions of years ago. The moon was not always the frozen world we see today. Its interior once moved, its rock melted, its magma rose, its surface cracked, and enormous volumes of lava spread across the landscape. Today, those lava plains look quiet, but they are frozen evidence of movement beneath our feet. And there is another clue. The moon is shrinking. Not dramatically enough for us to notice, not enough to make the ground suddenly collapse, but enough for spacecraft to detect evidence of geological contraction. As the moon's interior cools, the overall body can contract. That contraction can create faults in the crust. Long, steep cliffs appear across the surface. These are called lobate scarps. They can form when sections of the crust are pushed together as the moon becomes slightly smaller. The Lunar Reconnaissance Orbiter has photographed many such features. Some appear relatively young on geological timescales, and this creates a strange thought. The moon looks ancient, but it is not completely geologically frozen. Its interior is still cooling. Its crust is still responding, and its surface still records the consequences, even now. Billions of years after its formation, but cooling does something else. It changes how a world moves internally. Earth has a large, hot interior. Its mantle slowly circulates. Its outer core is liquid metal. That moving electrically conductive fluid helps generate Earth's global magnetic field. The moon is different. Today, it does not possess a strong global magnetic field like Earth's. But lunar rocks tell us something surprising. Some ancient lunar rocks are magnetized. That means the moon may once have had a much stronger magnetic field. If that is true, then something inside the moon must have once been moving in a way capable of generating it. A lunar dynamo. And that raises a remarkable question. How could a much smaller world generate a magnetic field billions of years ago? The answer may lie deep beneath the surface, far beneath the crust, far beneath the mantle, at the core. We cannot simply travel there. The deepest human drilling on Earth reaches only a tiny fraction of Earth's radius. On the Moon, no machine has ever drilled anywhere close to the core. So again, we have to listen. We have to measure gravity.
We have to study the Moon's response to Earth's pull. We have to analyze seismic waves, and we have to observe how the Moon physically moves through space. Gravity is especially useful. Every part of the Moon contributes to its gravitational field, but not equally. A dense region produces a stronger gravitational influence than a less dense region. If you orbit the Moon and measure tiny changes in your spacecraft's motion, you can detect variations in the gravitational field below you. This is exactly what NASA's Grail mission was designed to study. Grail used 2 spacecraft flying in formation around the Moon. As the distance between them changed slightly because of variations in the Moon's gravity, scientists could reconstruct those changes. The result was an extraordinarily detailed map of lunar gravity. And the map revealed something fascinating. The Moon is full of gravitational anomalies. Some correspond to enormous impact basins. Some reveal structures buried beneath the surface. Some indicate variations in crustal density and thickness. The Moon's surface may look like a landscape of mountains and craters, but underneath, it is another landscape, a landscape made of density, mass, rock, and hidden structures. It is invisible to your eyes, but gravity can see it. And one of the most striking discoveries came from the enormous impacts created by ancient impacts. When a massive asteroid or protoplanetary body strikes the Moon, it does more than create a crater. It excavates rock, it melts material, it fractures the crust, and it redistributes mass. Some of the largest impact structures extend hundreds of kilometers across. The South Pole Aitken Basin is one of the largest and oldest impact structures in the solar system. It stretches across a huge portion of the lunar far side. Its formation was so energetic that it may have excavated material from deep within the Moon's crust, and possibly even from the upper mantle. That means a gigantic impact billions of years ago may have performed something nature rarely allows us to do. It may have exposed material from deep inside the Moon. Not by drilling, by hitting the Moon hard enough. And that is why ancient impacts are so valuable. They are not simply scars, they are windows. A crater can tell us what existed beneath the surface before the impact. A large basin can expose deeper layers. A gravity anomaly can reveal dense material hidden underneath. And a seismic wave can travel through regions we could never physically reach. The Moon is therefore something like a natural laboratory. It lets us investigate planetary interiors without actually opening the planet. But there is a problem. The Moon does not behave exactly like Earth. Its seismic environment is different. Its internal structure is different. Its crust is different. And the Apollo seismometers produced results that were sometimes difficult to interpret. Some moonquakes appear to occur at great depths. Some are triggered by tides as Earth repeatedly pulls on the Moon. Some thermal quakes happen when the brutally cold lunar surface is suddenly heated by sunlight. The Moon can literally shake because sunlight reaches it. That alone is remarkable. Imagine the temperature changing rapidly across a surface exposed to space. Rock expands, rock contracts, stress accumulates, and the ground moves. But the deepest moonquakes are even more interesting. They occur far below the surface. The exact mechanisms and locations have been studied for decades, and because seismic waves interact with internal boundaries, these events can provide information about the Moon's interior. Yet there is a catch. The Apollo Seisma Network operated for only a limited period. The instruments were extraordinarily valuable, but the dataset was small compared to what we have for Earth. That means the moon's interior remains less precisely known than Earth's. Scientists can estimate its broad structure, but details remain uncertain, and those details matter.
Because the core is where the story becomes truly strange. For a long time, scientists debated whether the moon even had a core comparable to Earth's. Gravity measurements and other observations suggested that it did. But what kind? How large? How dense? How much sulfur or other light elements might it contain? Is the outer portion liquid? Is there a solid inner core? The answers matter because the core is a record of the moon's thermal evolution. A hot, moving, metallic interior can produce a magnetic field. A cooling interior gradually changes that ability. If the moon once possessed a global magnetic field, then the core must have remained long enough to generate it. But the moon is small. Small worlds lose heat more quickly. So the ancient lunar dynamo presents a puzzle. What powered it? Was it convection caused by cooling? Was crystallization of the core involved? Did the mantle and core exchange heat? Could tidal forces have contributed? Different models have explored different possibilities. And then came an important result. In 2023, researchers led by Arthur Briot and colleagues published a study in Nature using geophysical and geodetic evidence to model the lunar interior. Their results supported a lunar core with a solid inner portion and a fluid outer portion with dimensions broadly comparable to earlier estimates. But this does not mean scientists have simply seen the core. They have not. The result comes from combining measurements in physical models. It is an inference. And that distinction is important. Science does not require seeing something directly. We have never seen the center of Earth. We know about it because seismic waves, gravity, Earth's rotation, and other measurements constrain what can exist there. The same principle applies to the moon. The hidden interior leaves fingerprints, and those fingerprints can be read. But if the moon has a solid inner core, then something remarkable has happened. A world that appears cold and silent on the outside may still contain a metallic heart that has been slowly changing for billions of years. And that heart may preserve the last remnants of an ancient planetary dynamo. The moon may therefore have had a life cycle of its own. Birth, melting, differentiation, volcanism, magnetic activity, cooling, contraction, and gradual geological silence. But even that story may be incomplete, because the moon's interior is not simply interesting for understanding the moon. It may help answer a much larger question. How do rocky worlds evolve? Earth, Mars, Mercury, the moon, perhaps even planets orbiting other stars. All of them begin with some combination of rock, metal, heat, gravity, and time. And then they followed different paths. Earth remained active. Mars became colder and lost much of its global magnetic protection. Mercury retained an unexpectedly large metallic core. The moon became much smaller and cooled much faster. By comparing these worlds, scientists can learn what determines the fate of a planet. And the moon is especially valuable because it is close. We can send instruments there, we can return samples, we can observe its surface in extraordinary detail. And unlike Earth, its geological record has not been erased by oceans and plate tectonics. The moon has preserved evidence from an ancient solar system that Earth has largely destroyed. But perhaps the most valuable evidence is not on the surface at all. It may be buried, locked inside rocks, frozen in dark craters, encoded in gravity, or traveling invisibly through the moon as seismic waves. And there is one more problem. The moon's hidden interior may not be the only thing hiding beneath its surface. Some of the most intriguing discoveries concern enormous structures created by impacts. Structures so large that they can alter the moon's gravitational field. Structures that extend deep beneath the crust. And one of them lies near the lunar South Pole, the same region where scientists are searching for ancient ice. the same region that may preserve material from the earliest history of the Moon, the same region where future missions may spend years exploring. And beneath that ancient landscape is a geological scar so enormous that it may have changed the Moon itself. The South Pole Aitken Basin, a wound from the early solar system, and perhaps a window into what lies far beneath the surface.
The South Pole Aitken Basin is not simply a crater, it is a scar on the Moon so enormous that it is difficult to comprehend. It stretches roughly 2,500 kilometers across. That is about the distance from New York to Denver. And it reaches deep into the lunar crust. Scientists believe it formed more than 4 billion years ago, when the solar system was still young and enormous objects were moving through space at tremendous speeds. At that time, the Moon was being bombarded by debris left over from planetary formation. Asteroids, protoplanets, fragments of worlds that never became worlds. The young solar system was not a neat collection of planets moving peacefully around the Sun. It was a gravitational battlefield. Objects collided constantly. Some collisions created planets, some destroyed them, some changed their orbits, and some left scars that survived for billions of years. The South Pole Aitken impact was one of the largest. Imagine an object many tens of kilometers across, perhaps even larger depending on the assumptions used in different models, striking the Moon at enormous velocity. The energy released would have been beyond anything humans have ever produced. Rock would have been compressed, heated, melted, thrown outward. The surface would have been excavated, and material from deep below the surface could have been forced upward. This is important because the deeper we go into a rocky world, the older and more chemically distinct the material can become. The surface has been repeatedly altered. The deeper layers are protected. So an impact of this scale can act almost like a gigantic natural drilling machine. It does not drill neatly, it does something much more violent. It excavates. And that means the South Pole Aitken Basin may contain pieces of the Moon that normally would have remained hidden. Perhaps material from the lower crust, perhaps material from the upper mantle, and possibly material from depths that no spacecraft could ever reach by conventional drilling. But there is another reason scientists became fascinated by this basin: gravity. When NASA's Grail spacecraft mapped the Moon's gravitational field, they discovered extraordinary variations across its surface. Some of those variations correspond to structures created by ancient impacts. But beneath the South Pole Aitken Basin, there is something particularly unusual: a large gravitational anomaly, a region where the Moon's gravitational field is stronger than expected. Something dense is buried beneath the surface. We do not see it. We do not photograph it. There is no underground tunnel leading down to it. The evidence comes from gravity, and gravity is remarkably difficult to hide. Every piece of mass in the Moon contributes to the gravitational field. If a region contains unusually dense material, an orbiting spacecraft experiences a tiny change in acceleration as it passes overhead. The change is incredibly small, but spacecraft can measure it. And with enough measurements, scientists can reconstruct the distribution of mass beneath the surface. This is one of the most beautiful ideas in planetary science. You can discover something you cannot see by watching something else move. The spacecraft moves. The hidden mass pulls on it. The spacecraft's motion changes. And from that tiny change, scientists infer what is buried below. In 2019, researchers reported a large mass anomaly beneath the South Pole Aitken Basin using data from NASA's Grail mission combined with lunar topography. The study estimated that the anomaly could have a mass of roughly 2.18 times 10 to the 18th kilograms. That number is so large that it is almost meaningless to imagine directly. The researchers suggested one possible explanation: the dense material could be associated with the remnants of the metallic core of the impactor that created the basin. But they also considered other possibilities. The important point is not that we have discovered a buried metal object with certainty. We have not.
The anomaly tells us that there is an unusual concentration of mass beneath the basin. Its exact origin is an interpretation. And this distinction matters. Science often begins with an observation, then comes a model, then another model, then more measurements. The mystery is not removed, it becomes more precise. Perhaps the anomaly is related to the impactor. Perhaps it is associated with dense mantle material pushed into an unusual configuration. Perhaps several processes contributed. And perhaps future missions will tell us which explanation is correct. But think about what this means. There is something massive hidden beneath the moon. We know it's there because gravity gives it away, and it may have been created by an event that happened more than 4 billion years ago. A moment of violence so ancient that even before Earth had anything resembling its modern surface. And yet its gravitational fingerprint is still measurable today. The moon remembers. But there is something even stranger. The impact itself may have affected the moon's interior. A sufficiently large collision does not stop at the surface. Shock waves travel downward. Material is displaced.
The crust fractures. Heat is generated. The mantle responds. The distribution of mass changes. And if the moon was still partially molten when some of these ancient impacts occurred, the consequences could have been even greater. The early moon was not a rigid stone. It was evolving. Its crust was forming. Its mantle was separating. Its interior was cooling. A giant impact could therefore have interacted with a world whose internal structure was still changing. That makes the South Pole Aitken Basin more than a crater. It could be part of the moon's geological biography, a chapter written in a single violent moment. And yet the basin is only one piece of a much larger puzzle. Because when scientists map the moon globally, another pattern becomes impossible to ignore. The moon has two faces, not simply two sides, two geological personalities. The near side is dominated by dark volcanic plains. The far side is dominated by rugged highlands and enormous numbers of craters. Why? At first, you might imagine the explanation is simple. Perhaps the near side was struck by more asteroids. Perhaps the far side simply experienced fewer volcanic eruptions. But the difference is too systematic to dismiss so easily. The crust itself is different. The near side has a thinner crust in many regions. The far side generally has thicker highland crust. The distribution of certain radioactive elements is also strongly asymmetric. And the volcanic history is dramatically different. This is one of the moon's oldest unresolved questions. Why did a world that formed from essentially the same broad body develop such different hemispheres? One possibility involves the moon's early thermal history. When the magma ocean crystallized, some elements became concentrated in the remaining melt. Among them were heat-producing radioactive elements. If those elements became concentrated preferentially on the near side, they could have contributed to prolonged heating there. More heat means a greater possibility of partial melting. More partial melting means more magma, and more magma reaching the surface means more volcanic plains. This could help explain why the near side became so much darker. But why would the radioactive elements become concentrated on one hemisphere? Now the problem becomes deeper. Perhaps the asymmetry developed very early. Perhaps the moon's crust crystallized unevenly. Perhaps tidal effects from Earth influenced the thermal evolution. Perhaps enormous impacts changed the distribution of heat in material. Or perhaps several processes worked together. Scientists are still investigating, and this is where lunar science becomes fascinating, because the moon is close enough that we can observe these differences in detail. But it is old enough that the clues have survived for billions of years. The far side is especially valuable. For a long time, popular culture called it the dark side of the moon. That phrase is misleading. The far side receives sunlight. It is not permanently dark. The moon rotates, and sunlight illuminates both hemispheres over the course of its orbit. The far side is simply the side we normally cannot see from Earth. And that distinction is more than a technical detail. It changes how we imagine the moon. The far side is not another world. It is part of the same world, but it developed differently, and that difference may tell us something about the moon's interior. Think about a planet. Its surface reflects what happens inside. Volcanoes reveal internal heat. Mountains reveal stresses. Magnetic fields reveal moving conductive material. Gravity anomalies reveal hidden mass. And the chemistry of rocks reveal the conditions under which those rocks formed. The moon's two faces are therefore like two pages from the same book. The near side contains one story. The far side contains another. And to understand both, we need to understand what happened when the moon was young. Return again to that ancient magma ocean. The moon is thought to have begun with a large amount of molten material. As the magma cooled, crystals formed. Some crystals were dense and sank. Others were less dense and rose. This process is called fractional crystallization. It sounds simple, but the chemistry can become complicated. Imagine a huge volume of molten rock. As certain minerals crystallize, they remove particular elements from the liquid. The remaining liquid therefore changes composition. It becomes enriched in elements that do not easily fit into the early forming crystals. Eventually, the last portions of melt may become chemically very different from the original magma. And some of those late-stage materials may have been relatively rich in heat-producing elements. This creates a possible path toward the moon's strange asymmetry. But then comes the problem of stability. If dense material ends up above lighter material, gravity does not like the arrangement. The system is unstable. Imagine placing a layer of heavy fluid above a lighter fluid. The heavy fluid wants to sink. The light fluid wants to rise. In a planetary mantle, the same basic physics can operate on a vastly larger scale. This may have happened inside the young moon. Dense, late-forming materials could have sunk. Hotter, lighter material could have risen. The mantle may have overturned. And if this occurred, it would have redistributed heat and chemical elements inside the moon. The moon would effectively rearrange itself. Not at once, not like a solid ball turning inside out, but through slow, enormous flows of material over geological time. And those flows could have helped determine what eventually appeared at the surface. The moon's current appearance may be partly the result of an ancient internal instability, a process that began when the moon was still young enough to be hot. That is a remarkable thought. The craters we see today are obvious, but some of the most important events shaping the moon may have happened without leaving a crater at all. They happened underground. Rock moved, heat moved, elements moved. The mantle changed, the crust changed, and billions of years ago we can still see the consequences. But now another question appears. If the moon was once largely molten, how did it become a rigid world we see today? How did an ocean of magma become mountains? How did molten rock become a crust strong enough to preserve impacts for billions of years? And what happened to all that heat? The answer begins with cooling. A world loses heat in stages. At first, cooling can be rapid. The surface radiates energy directly into space. A crust forms. Beneath it, the interior remains hot. Over time, the temperature difference between the surface and interior drives changes. The moon becomes more rigid. The mantle becomes less capable of large-scale movement. Volcanism gradually decreases. The core evolves. The magnetic field weakens. And eventually, the moon approaches the state we know today. But it never becomes perfectly static, because temperature is not the only force acting on it. Earth is still there, and Earth is enormous compared with the moon. The moon feels Earth's gravity continuously, and Earth's gravity does not pull equally on every part of the moon. The side of the moon facing Earth is slightly closer. The far side is slightly farther away. That difference produces tidal forces. We see the effect dramatically in Earth's oceans, But tides also deform solid rock. The moon itself is constantly being stretched and squeezed by Earth's gravity. The deformation is small, but over billions of years, small effects can become important. Tidal forces influence the moon's rotation. They helped establish its synchronous rotation. They influence its orbit, and they may have contributed to the moon's internal heating early in its history. The moon is therefore not an isolated object. It is part of a gravitational system. Earth pulls on the moon pulls on Earth. The two worlds exchange angular momentum. The moon slowly moves away from Earth. Earth's rotation gradually slows. And all of this happens because gravity is not simply a force that keeps the moon in orbit. It is a force that changes both worlds. The moon is still responding to Earth, even now. And that means the story beneath the moon is also connected to something beneath our own feet. Because the moon's evolution has influenced Earth. Its tides helped shape Earth's oceans. Its presence stabilizes Earth's axial orientation to some degree. Its orbital history is connected to the rotation of our planet. The moon is therefore not merely a satellite, it is part of Earth's long-term evolution. And perhaps the strangest part is that we may never have had this particular Earth without this particular moon. Which brings us back to the beginning. The moon formed from violence. It cooled from a molten state. It separated into layers. It developed a crust. Its mantle moved. Its core evolved. Its magnetic field appeared and faded. Asteroids carved enormous scars across its surface. Water became trapped in permanent darkness. And beneath one of its oldest impact basins, an enormous mass remains hidden from direct view. But there is still something missing from the story. We know what the moon looks like today. We have a reasonable idea of its broad internal structure. We can reconstruct parts of its ancient history, but we do not yet know exactly how the moon's deepest interior behaves. And that matters because the deepest interior may contain the final clues to one of the moon's greatest mysteries. How did a small world manage to have a magnetic field? How long did that field last? What powered it? And what exactly happened when the lunar dynamo finally began to die? To answer that, we have to go deeper still, past the crust, past the ancient mantle, past the regions where magma once flowed, toward the metallic center. And down there, beneath thousands of kilometers of rock, the moon may still be carrying the memory of the magnetic field it lost billions of years ago. Deep beneath the moon's crust, beneath the ancient volcanic plains and the fractured mantle, lies something very different from the rock above it: metal. The moon has a core. We cannot see it. No spacecraft has traveled anywhere near it. No drill has come remotely close. And yet scientists can estimate its structure from the way the moon moves, responds to gravity, and carries seismic waves through its interior. The moon's core is small compared with the Earth's core, but small does not mean unimportant. In fact, the core may contain one of the most important clues to the moon's past, because the moon once had something it no longer has: a global magnetic field. Today, if you stood on the lunar surface with a compass, you would not find a strong global magnetic field guiding the needle the way Earth's magnetic field does. The moon does have localized magnetic regions. Some areas of its crust are magnetized, but there is no strong planet-wide lunar magnetosphere surrounding the moon today. Yet ancient lunar rocks tell us that things were very different billions of years ago. Some samples collected during the Apollo missions contain remnant magnetization. The minerals inside those rocks preserve evidence that they formed or cooled in the presence of a magnetic field. This is one of the most remarkable forms of planetary memory. A magnetic field is invisible. You cannot photograph it in an ordinary image. You cannot touch it. But when certain minerals cool through particular temperatures in a magnetic environment, their magnetic moments can become aligned. Later, the rock carries a record of that ancient field. The rock becomes a tiny geological compass frozen in time. And lunar rocks appear to contain such records. This means that the Moon once had an active magnetic environment much stronger than the one we see today. But now we encounter a problem. Where did the magnetic field come from? On Earth, we have a reasonably strong explanation. Deep inside Earth's is a liquid outer core, rich in iron and other elements. Earth's rotation and the movement of that electrically conductive fluid create a dynamo. Moving conductive material generates magnetic fields. The result is Earth's global magnetic field. But the Moon is much smaller. Its interior cooled more quickly, and today its core is far less energetic. So what powered its ancient dynamo? Several mechanisms have been proposed. Perhaps the early Moon had enough residual heat to drive convection in its liquid core. Perhaps as the core cooled and crystallized, chemical differences drove movement. Perhaps tidal interactions with Earth contributed energy. Perhaps the lunar dynamo changed its strength and behavior over time, rather than simply switching on and off. The evidence suggests the ancient field may have been surprisingly strong, but its exact history remains debated. And that uncertainty is important because scientists are not simply trying to determine whether the Moon once had a magnetic field. They are trying to reconstruct its entire life. When did the dynamo begin? How strong was it? How long did it survive? Did its strength rise and fall? Did it reverse direction? What eventually stopped it? Each question tells us something about the interior, and the answer may also tell us something about how small rocky worlds lose their internal energy. Imagine the young Moon. The surface is beginning to cool. The interior is still hot. The core contains molten metal. The mantle above it is slowly changing. Heat flows outward. The core responds. Convection begins. Hot material rises. Cooler material sinks. The moving metal generates a magnetic field. For a time, the Moon has a magnetic shield. Then the interior gradually changes. The available energy decreases. The core cools. Material begins to crystallize. The pattern of movement changes. The dynamo weakens. Eventually, the global field fades. The Moon becomes magnetically quiet.
But when did this happen? That question is surprisingly difficult. Different lunar rocks preserve magnetic signals from different periods. Some evidence suggests the lunar dynamo existed very early. Other measurements indicate that a magnetic field persisted for a surprisingly long time. There may even have been different phases of dynamo activity. A 2017 study in Science Advances, for example, found evidence from lunar rocks suggesting that the Moon's magnetic field remained active much longer than many earlier estimates had assumed. The researchers examined the magnetic record preserved in Apollo samples and argued that the lunar dynamo may have persisted until roughly 1 billion years ago, although the exact timeline and mechanisms remain an active area of research. That is an extraordinary possibility. If the Moon's magnetic field lasted for billions of years, then its small core remained dynamically active for an unexpectedly long portion of lunar history. But then another question appears. Why did it stop? Because a dynamo does not simply disappear because a planet becomes old. Something physical has to change. The energy available to drive the motion must decrease. And this takes us into one of the deepest ideas in planetary physics: heat. A planet is not simply hot or cold. It contains an energy budget. Some of that energy was inherited from formation. Some came from impacts. Some came from gravitational compression. Some comes from radioactive decay. And some is released as the interior separates into layers. Over time, energy escapes through the surface. The world cools. But the rate at which it cools depends on size, composition, structure, and efficiency of heat transfer. Earth is large. The Moon is much smaller. That difference matters. Imagine two pieces of hot rock. One is the size of a mountain, the other is the size of a small stone. Both begin at the same temperature. The smaller one has a much larger surface area to volume ratio. It can lose heat more efficiently. The Moon is not literally a stone in this simple sense, but the same basic geometric principle matters for planetary cooling. Small worlds generally lose their internal heat faster than large worlds.
Mars is smaller than Earth and lost its global magnetic field long ago. The Moon is smaller still. Its ancient dynamo therefore faced a difficult future. But there is another factor. The Moon's core may have contained light elements mixed with iron. As the core cooled, iron could begin crystallizing. And when solid material forms from a liquid mixture, the composition of the remaining liquid can change. That can create chemical buoyancy. A fluid with a different composition can become lighter or heavier than the surrounding material. So crystallization itself can potentially drive motion. This is one of the mechanisms considered in models of planetary dynamos. On Earth, the growth of the solid inner core releases both latent heat and light elements into the liquid outer core. That helps drive convection. The Moon may have experienced a different version of this process, but the Moon's core is much smaller. Its thermal history is different, its composition is less well known, and its dynamo appears to have followed a different path. So scientists are effectively trying to solve a puzzle with missing pieces. They know the magnetic field existed. They know it later became weak. They can estimate properties of the core, but they do not have a perfect record of the transition. And that is where the ancient rocks become so valuable. Every magnetized lunar sample is a timestamp. A small fragment of rock can preserve information about the magnetic environment that existed when it formed or cooled. Scientists can measure the direction and intensity of its magnetization. Then they compare samples from different ages. If an older rock contains a strong magnetic signal and a younger one contains a weaker one, the dynamo may have been declining. If different samples show different field directions, the field may have changed. If the magnetization varies strongly with age, the Moon's magnetic history may have been dynamic rather than simple. The Moon's rocks therefore become something like pages in a magnetic diary. But the diary has missing pages. The Apollo missions sampled only a small number of locations. The Moon is enormous compared with those landing sites, and many of the oldest regions remain unexplored directly. Future missions could therefore change the story. A rock from a different basin might preserve a magnetic signal from a different period. A sample from the far side might reveal something completely unexpected. A sample excavated from a deep impact structure could contain material from much deeper layers. The Moon has billions of years of history. We have sampled only tiny pieces of it. And perhaps the greatest limitation is that most lunar samples came from the near side. The far side remains much less directly sampled. That is beginning to change. Modern lunar exploration is moving toward regions that were almost impossible to reach during the Apollo era. The lunar South Pole is particularly important, not simply because of water, because the poles contain terrain that is ancient, complex, and poorly sampled. Some craters there have remained permanently shadowed. Some areas receive unusual patterns of sunlight. The crust has been heavily impacted, and beneath the surface may lie material excavated from enormous ancient collisions. A future sample from the right location could potentially connect several mysteries at once: the Moon's water, its impact history, its ancient crust, its interior, its thermal evolution, its magnetic past, all from a few kilograms of rock. This is why lunar science is so much more than photographing craters. A single rock can contain a history that begins billions of years ago. But there is another instrument that has already given us a remarkable view into the Moon: the seismometer.
When an earthquake happens on Earth, seismic waves can travel through the planet. Scientists use them to determine Earth's internal structure. The Moon works similarly, but lunar seismic activity behaves in unusual ways. The Moon can experience deep moonquakes caused by tidal stresses from Earth. It can experience thermal quakes caused by rapid heating. It can experience impacts, and it can experience shallow moonquakes associated with tectonic stresses. The Apollo instruments recorded these events for years, and something about the Moon became clear. It is not silent. It moves. It vibrates. It responds. Its interior is still active enough to produce detectable seismic signals. One particularly strange property of the Moon is that seismic vibrations can persist for a long time.
On Earth, an earthquake's energy is dissipated through fractured, warm, and relatively heterogeneous rock. The Moon's dry interior behaves differently. It is much more rigid and heavily fractured. Energy can reverberate. The result is sometimes described as the Moon ringing like a bell. That phrase can be misleading if taken literally. The Moon is not a hollow bell. But the analogy captures something real. Seismic energy can persist much longer than it typically does in Earth's crust. And that behavior itself tells us something about the material inside. A dry, fractured world transmits seismic energy differently from a wet, tectonically active world. The Moon's interior, therefore, has a kind of seismic fingerprint. The waves tell us not only where boundaries may exist, they tell us about the physical properties of the material they travel through. But the most important question is not simply how the Moon rings. It is what those vibrations reveal. When a seismic wave reaches a boundary between two materials, its behavior changes. Part of the energy can be reflected. Part can pass through. The speed can change. The direction can change. If enough measurements are available, scientists can reconstruct the layers. This is how the Apollo seismic data helped establish that the Moon is differentiated: crust, mantle, core. But the data also revealed something unexpected. The Moon's crust is fractured and heterogeneous. Its interior is not a perfectly smooth set of concentric shells. Impact after impact has disturbed it. Large basins have excavated and compressed material. Ancient volcanic activity has filled some regions with basalt. Cooling has created faults. Tidal forces have stressed the body. The Moon is therefore a geological record that has been repeatedly edited. Yet beneath all those changes is a deeper structure: the original differentiation of the Moon, the separation of rock from metal, the formation of the core, the creation of the mantle, the freezing of the magma ocean. Those events happened very early, and much of their evidence remains hidden below the surface. That is why scientists are interested in going deeper, not physically drilling all the way down, but using increasingly sensitive measurements: laser ranging, gravity mapping, seismic networks, magnetic observations, heat flow measurements, high-resolution topography, and eventually, perhaps, new samples. Each technique sees a different aspect of the hidden Moon. Gravity sees mass. Seismology sees structure. Magnetism sees ancient fields and magnetic minerals. Spectroscopy sees chemistry. Topography sees shape. Samples reveal physical material directly. And when all these methods agree, confidence increases. When they disagree, the mystery becomes more interesting, because disagreement often tells scientists that the model is incomplete. The Moon's core is one of those places where the picture is improving but not finished. We now have strong evidence for a metallic core and compelling evidence for a solid inner portion, but the exact composition remains uncertain. Iron is important, but pure iron is unlikely to explain all the measurements. Sulfur and other light elements may be present. The core may have a liquid outer region. The inner core may be solid. The dimensions are constrained but not known with the precision we have for Earth's interior. And there may be subtle layers we have not yet detected. The Moon could still surprise us. But perhaps the most important question is not what the core contains. It is what the core tells us about time. Because every planetary interior changes. The Moon's core was once hotter. Its mantle was once more active. Its magnetic field was once stronger. Its surface was once volcanic. And eventually, all of those processes slowed. The Moon is a record of cooling, a world caught at one stage of planetary evolution. And if we understand how it cooled, we can better understand how other rocky worlds cool. That includes Earth, it includes Mars, it includes Mercury, and potentially rocky exoplanets orbiting distant stars. A small moon can therefore teach us something about planets we cannot even visit. But there is a final twist. The Moon may not have simply cooled from the outside inward. Its interior may have changed in complicated stages. core crystallization, mantle convection, magma generation, volcanic eruptions, tidal heating, impact heating, radioactive decay. Each process adds or removes energy. Each changes the structure. And the timing matters. If the lunar dynamo was active for a long time, something must have continued supplying enough energy to move the core. If the field weakened in stages, perhaps the core itself evolved in stages. And if the field eventually disappeared, perhaps that disappearance marks a major transition in the moon's interior. So when we look at the moon tonight, we are not looking at a dead object. We are looking at the cooled remains of a world that once had a molten exterior, a moving mantle, volcanic eruptions, a magnetic field, and a violently active interior. The visible moon is the final layer. The hidden moon is the history, and that history is written in a language we cannot read simply by looking at the surface. We need waves, we need gravity, we need magnetism, we need chemistry, and sometimes we need darkness. Because some of the most important material on the moon may be preserved in places where sunlight has almost never reached. And if those deposits contain ancient water and other volatile compounds, they could become something even more valuable than a resource. They could become a record of what has been arriving on the moon for billions of years. Comets, asteroids, solar particles, interplanetary dust, perhaps material released by ancient impacts. The moon may have been quietly collecting pieces of the solar system for almost its entire existence, and unlike Earth, it did not have oceans and an atmosphere to erase them. Which means that the next mystery is not deep beneath the moon. It may be hidden in the coldest places on its surface, places where the sun never rises, places where ancient material can remain frozen, places where the moon may have been keeping a record, waiting for us to finally uncover it. The moon's magnetic field may not have simply faded away. It may have come and gone. For a long time, scientists imagined a relatively straightforward story. The young moon was hot. Its core contained liquid metal. That metal moved. The movement generated a magnetic field. Then the moon cooled. The core became less active. The magnetic field weakened, and eventually it disappeared. It is an elegant story, but nature does not always choose elegant stories. Recent research is suggesting that the ancient lunar dynamo may have been much more complicated. A 2026 study in Nature Geoscience proposed that strong lunar magnetic fields between roughly 3.854 and 3.580 billion years ago may have occurred intermittently and may have been connected to periods of high titanium volcanic activity. The authors modeled heat flow between the lunar core and mantle and proposed that unusual melting processes near the core-mantle boundary could have helped generate episodes of dynamo activity. If this interpretation is correct, then the moon's magnetic history was not simply a candle slowly burning out. It may have flickered. On, off, perhaps on again. And that changes the question. We are no longer asking only, why did the moon lose its magnetic field? We are asking, why did the moon's interior sometimes become capable of generating one? The answer may involve something unexpected: volcanic rock, high titanium basalt, and a mineral called ilmenite. Ilmenite contains iron and titanium. During the moon's early history, enormous amounts of titanium-rich basalt erupted onto the surface. These dark rocks became some of the material that makes the lunar Maria look so different from the bright highlands. For a long time, scientists mainly thought of these basalts as evidence of ancient volcanic activity. But they may have another story to tell. The chemistry of those rocks can preserve information about the moon's interior. Because volcanic material does not appear from nowhere, it comes from melting inside the moon. And where something melts tells us about the temperature, composition, and physical state of the mantle. So when scientists discover that magnetic evidence and high titanium volcanic rocks occur in related periods, they begin to wonder whether the two processes were connected. Perhaps the interior was reorganizing itself. Perhaps dense titanium-rich material accumulated deep inside. Perhaps some of it later became gravitationally unstable. And perhaps that instability changed the flow of heat at the boundary between the mantle and the core. The core sits beneath the mantle. Heat wants to escape from the core. If the rate and pattern of heat transfer change, the movement of liquid metal inside the core can change. And if that movement changes enough, the magnetic field can change. A tiny difference deep inside the moon could therefore produce a completely different environment above it. That is the extraordinary thing about planetary interiors. The surface may be hundreds or thousands of kilometers away from the process that ultimately controls it. A person standing on the moon would see nothing unusual. The sky would remain black. The ground would remain gray. The sun would shine. But far below, the movement of metal could be changing, and the consequences would extend into space. A magnetic field is not merely something that surrounds a planet. It changes how charged particles interact with that world. The young sun was more active than today's sun. Its solar wind was stronger. Its radiation environment was harsher. A magnetic field could influence how the lunar environment responded. So the moon's ancient dynamo may have affected more than the interior. It may have changed the space environment immediately surrounding the moon. But there is an even stranger possibility. The moon may have generated magnetic fields at different times for different reasons. Early in its history, one mechanism may have dominated. Later, another may have taken over. Core convection, core crystallization, mechanical interaction between the mantle and the core, tidal effects, perhaps large impacts, perhaps episodic changes in mantle structure. A small world can have more than one way to generate a magnetic field over its lifetime. And this is where the moon becomes a laboratory for planetary physics. Earth has an active dynamo today. Mercury still has a global magnetic field despite being much smaller than Earth. Mars has localized crustal magnetism, but no present-day global dynamo. The moon preserves evidence that it once had its own. Each world represents a different stage in the evolution of rocky bodies, and perhaps the moon is telling us something fundamental.
A magnetic field is not necessarily a permanent feature of a planet. It is a phase, a consequence of conditions inside the world. Change those conditions, and the field changes. But then we encounter another mystery. If the moon's dynamo was intermittent, what switched it on and what switched it off? The answer may be hidden in the movement of material inside the mantle. Imagine the young moon after the magma ocean began to crystallize. Dense minerals formed. Some sank. Lighter materials rose. But the process did not necessarily stop once the crust solidified. The moon's interior could continue rearranging itself. Dense material could sink toward the core. Hot material could rise. This is convection. On Earth, mantle convection operates extremely slowly. A piece of rock can take millions of years to travel through a mantle. The movement is almost impossible to imagine because the material is solid on human timescales. But over geological time, solid rock can flow. The moon's mantle may have done the same, and if its internal structure changed, so did its ability to transport heat. This is crucial. The core cannot generate a magnetic field simply because it contains metal. The metal must move in the right way. A stationary block of iron does not create a global dynamo. The fluid must circulate. Heat must escape. Energy must drive motion. The geometry of that motion matters. The composition matters. The rotation matters. The state of the core matters. The moon, therefore, needed a delicate combination of conditions, and those conditions could change.
Perhaps a particular phase of mantle overturn increased the heat leaving the core. The core responded. Convection strengthened. The magnetic field intensified. Then the mantle evolved. The heat flow changed. The dynamo weakened. Later, another internal process could have altered the balance again. The field returned. This is one possible interpretation of the newer research. It remains a model, not a final answer. But models are valuable because they tell us what observations would matter next. If the moon's dynamo really was intermittent, lunar rocks from different ages should preserve different magnetic histories. And that means the next generation of lunar exploration could test the idea. A rock does not need to be alive to remember. It only needs to contain the right minerals. As molten rock cools, magnetic minerals can record the surrounding magnetic field. If the field is strong, the record can be strong. If the field is weak, the record can be weaker. If the field has a particular direction, the magnetic grains can preserve that orientation. The result is a kind of geological photograph, not a photograph of the moon's surface, a photograph of an invisible field, frozen inside stone. And now imagine collecting samples from several different periods, a very ancient sample, another from a later volcanic eruption, another from a still younger basalt. If their magnetic records differ, the moon's magnetic history begins to emerge. The moon becomes a timeline. Each rock marks a moment. Each crystal preserves a clue. And suddenly the question of what is hiding beneath the moon becomes a question about time. Because the hidden moon is not just a place, it is a sequence of states. A hot moon, a molten moon, a volcanic moon, a magnetic moon, a cooling moon, a shrinking moon, a moon with frozen polar reservoirs, and eventually the quiet moon we see today. But there is something else that happened while the interior cooled. The moon became smaller, not by a dramatic amount, not enough for the moon to visibly change from one night to the next, but enough for its crust to respond. As the interior loses heat, it contracts. The total volume of the moon decreases slightly. The rigid crust can simply disappear. Instead, it has to adjust. Sections of crust can be pushed together. Faults can form. One block can move over another, and these movements leave cliffs across the lunar surface. Some of these features are called lobate skarks. They are among the clearest signs that the moon has undergone global contraction, and some may be relatively young. That is an extraordinary thought. The moon is billions of years old, yet parts of its surface may have experienced geological deformation comparatively recently. The moon has not been completely frozen in time. It is still responding to its cooling interior. And cooling does not happen smoothly. Different regions can cool at different rates. Different materials expand and contract differently. Impact basins weaken the crust. Volcanic deposits alter its structure. Earth's gravity continually pulls on the moon. The result is a world under stress. Most of that stress is invisible until the ground moves. Then we get a moonquake. The moon can shake because its interior is changing. It can shake because Earth pulls on it. It can shake because an asteroid strikes it. And it can shake because sunlight heats the surface after a long lunar night. That last one is particularly strange. On much of the moon, the surface experiences roughly 2 weeks of sunlight, followed by roughly 2 weeks of darkness. During the lunar day, exposed surfaces can become extremely hot. During the lunar night, they become extremely cold. Rock expands. Rock contracts. Over repeated cycles, stress builds. The result can be measurable seismic activity. The moon is therefore not silent. It is constantly responding to its environment. But now imagine listening to those vibrations with a much larger network of instruments. Not just a few seismometers, dozens, perhaps hundreds spread across the lunar surface. Then the moon would become something like a gigantic natural medical scan. A moonquake would send waves through the interior,
Different waves would travel through different materials. The instruments would record their arrival times. Scientists could compare the signals. They could locate the source. They could trace the paths. They could identify boundaries. And eventually, they could build a much sharper image of the hidden moon. This is why future lunar seismology could be transformative. The Apollo instruments gave us the first glimpse. Future networks could provide something much closer to a full internal map. And that map might reveal details we cannot infer confidently today. Perhaps another layer inside the core. Perhaps variations in the mantle. Perhaps ancient structures created by giant impacts. Perhaps unexpected regions of partially molten material. The moon could still have surprises waiting below. But there is an even more unusual property of the lunar surface. The moon can ring. Not like a bell made of metal, but in the sense that seismic energy can persist and reverberate through its dry, fractured interior. Apollo experiments demonstrated that impacts and moonquakes could produce long-lasting seismic signals. The absence of Earth's atmosphere, oceans, and active plate tectonics is important here. The moon's interior is cold and dry compared with Earth's active interior. Its crust has been heavily fractured by billions of impacts. Those fractures can scatter seismic energy. Instead of rapidly disappearing, waves can reverberate through the body. The moon behaves differently from Earth because the two worlds have evolved differently. And that difference gives us another window. A seismic signal is not merely an earthquake, it is a probe. It travels through the planet, and by the time it reaches a detector, it has interacted with everything along its path. The signal has been changed by the material it crossed, its speed, its amplitude, its frequency, its direction. All of those changes carry information. This is why seismology is so powerful. The instrument does not need to travel to the core, the wave does the traveling. And that is one of the recurring themes of lunar exploration. We do not have to physically reach the hidden world. We can send information through it. Gravity passes through. Seismic waves pass through. Heat travels outward. Magnetic fields extend into space. Light reflects from the surface. The moon is constantly revealing itself without opening itself. And then there is another kind of signal, water. The polar regions are cold enough to trap it. NASA's current lunar science information confirms water ice in permanently shadowed regions and also notes water molecules on sunlit terrain. Scientists are still investigating how lunar water arrived and how it moves across the surface. The simplest picture would be that water arrived from comets, but that is probably not the entire story. Asteroids can deliver water. Micrometeorites can contribute. The solar wind can interact with the lunar surface and help produce or modify water-bearing molecules. Impact processes can redistribute material, and some water may migrate across the surface over time. A water molecule exposed to sunlight does not necessarily remain where it started. It can be released. It can move. It can become trapped again in a cold region. Over enormous periods of time, the moon can act like a giant chemical sorting system. Sunlight provides energy, the cold traps it away, and the polar landscape determines where molecules can survive. That means the ice may not simply be a frozen lake that has existed unchanged since the moon formed. Some of it could have accumulated later, some could have migrated, some may be relatively young, some may preserve older material. And separating these possibilities is extremely important. Because if the ice is a record of the solar system, we need to know what kind of record it is. Is it a continuous archive, or has it been repeatedly rewritten? Is it ancient, or mostly recent? Does one crater contain material deposited at a different time from another? Could different layers preserve different eras? The answer may eventually come from drilling. Not thousands of kilometers, just meters, perhaps tens of meters. Because the surface of the moon is constantly exposed to space, radiation, solar wind, micrometeorites, temperature changes. But deeper material is more protected. A drill could therefore move through layers of lunar history, top layer, then another, then another. Each layer could contain a different chemical story. Imagine a future instrument lowering a drill into permanently shadowed ground. The machine disappears into darkness. It cuts through frozen material. It measures temperature. It measures composition. It detects gases. It encounters ice. And then perhaps it reaches a layer that has been sealed away for an enormous amount of time.
What would it contain? Water from ancient impacts? Volatile compounds? Chemicals delivered by comets? Particles from the sun? Or something we have not anticipated? We do not know. And that uncertainty is precisely why the lunar poles have become such important targets. NASA has already demonstrated lunar drilling technology through the Prime 1 experiment, designed to investigate the lunar South Polar region and test technologies for working with subsurface material in permanently shadowed environments. The South Pole is therefore becoming more than a scientific location. It is becoming a gateway, a place where the moon's surface, interior, history, and future exploration all intersect. And beneath those permanently shadowed craters may be something even more valuable than water. Time. Not time as a physical dimension, but preserved evidence of what happened long ago. Because Earth is terrible at keeping ancient surface records. Our planet is alive. Oceans move, continents drift, mountains rise and erode, rocks melt, crust disappears into the mantle, new crust forms. The atmosphere changes. Life modifies the surface. The Earth constantly destroys its own history and replaces it. The Moon does almost none of this. That makes it a geological archive, a fossil, a frozen witness. And perhaps that is the deepest reason we keep returning to it, not because it is merely close, not because it is beautiful, not because humans once walked there, but because the Moon may remember things that Earth has forgotten. And the further we investigate, the more the Moon begins to look less like a companion hanging in the night sky, and more like a surviving fragment of the early solar system. A fragment with a molten past, a magnetic past, a volcanic past, a violent past, and perhaps, hidden in its rocks and ice, a record of the young Earth itself. Because the Earth and Moon did not evolve separately. They began together. They shared the same ancient environment. They were shaped by the same impacts. And for a period in the distant past, the Moon and Earth were much closer to each other than they are today. The tides were stronger. Earth rotated faster. The gravitational interaction between the two worlds was far more intense. And that ancient relationship may have affected the Moon's interior. It may have affected its rotation. It may have affected its thermal evolution. It may even have influenced some proposed mechanisms for its ancient dynamo. The Moon's history is therefore not just lunar history, it is Earth-Moon history. And if we want to understand what is hiding beneath the Moon, we may eventually have to ask an even larger question. What is the Moon hiding about Earth? Because somewhere beneath the lunar surface may be material that formed when both worlds were still young. Somewhere in its ancient rocks may be chemical evidence of conditions that no longer exist on Earth. Somewhere in its polar deposits may be a record of billions of years of impacts. And somewhere deep inside its core may be the final remains of the processes that once made the Moon magnetically alive. We have spent decades uncovering pieces of this story, but we have not yet assembled all of them. And perhaps the next clue will not come from another photograph. It may come from a rock, a seismic wave, a gravity measurement, a drill, or a place on the far side of the Moon where no human has ever stood. Because the Moon still has an entire hemisphere that we have barely touched. And beyond that hemisphere, beneath the ancient crust, the deepest part of the story is still waiting. There is another reason the Moon is so valuable. It is not only because we can study what happened to the Moon, it is because the Moon can help us understand what happened to Earth. Earth and the Moon are not independent stories. Their histories are intertwined. The Moon's gravity has been pulling on Earth for billions of years. The Earth has been pulling on the Moon. Their orbits have changed. Earth's rotation has changed. The Moon has slowly moved farther away, and the ancient Earth was very different from the planet we know today. Its surface has been repeatedly destroyed and rebuilt. Continents moved, oceans opened and closed. Mountains rose, mountains disappeared. Crust was recycled into the mantle.
Even rocks that existed billions of years ago are relatively rare. The Moon did not experience this same level of geological recycling. There are no Earth-like plate tectonics covering its surface, no global ocean constantly eroding the landscape, no thick atmosphere driving a planetary weather system, no biosphere continuously transforming the chemistry of the surface. The Moon preserved much more of its ancient record. That makes it something extraordinary, a geological archive sitting beside Earth. And some of the oldest rocks on the Moon are older than almost any rock that remains exposed on our planet. That means when scientists study lunar material, they are sometimes studying conditions from a period of solar system history that Earth itself has largely erased. The Moon is not simply telling us what happened there, it is helping us reconstruct a world that no longer exists. The young Earth, the young Moon, the violent solar system around them, and perhaps the enormous collision that created the Moon itself. That collision remains one of the great stories of planetary science. The leading giant impact hypothesis proposes that the young Earth was struck by a large planetary body, often called Theia. The impact would have released enormous amounts of energy. Material from Earth and the impactor was thrown into orbit. That material eventually gathered together, and from it, the Moon formed. But even after decades of study, important questions remain. Exactly how much material came from Earth? How much came from the impactor? How rapidly did the Moon assemble? Was the initial Moon completely or largely molten? How quickly did it move away from Earth? And how did its initial composition become what we see today? The Moon contains clues, but clues are not always answers. Sometimes the most interesting discovery is simply realizing that an old explanation is incomplete, and this is happening repeatedly in lunar science. We once thought the Moon was completely dry. It isn't. We once thought it was geologically dead. It isn't completely dead. We once imagined its magnetic history is relatively simple. It may have been much more complicated. We once thought of the far side as simply the side we could not see. Now we understand that it is geologically different. We once thought the Moon's surface was simply ancient dust and rock. Now we know that the surface is constantly being modified by impacts, solar radiation, and interactions with the solar wind. And beneath all of this is a world whose interior is still changing, perhaps very slowly, but not zero. That distinction matters. The Moon is not frozen in time. It is evolving. Its interior continues to lose heat. Its crust continues to respond. Its surface continues to be struck. Its exosphere continues to change. Water molecules can move. Dust can be lifted. New impacts expose material that was previously buried. The Moon is quiet, but quiet is not the same as inactive. And there's something almost poetic about that. Because when we look at the Moon from Earth, we see a world that appears completely still. Yet every moment, particles from the Sun are striking it. Every moment, gravity is pulling on it. Every moment, its interior is slowly losing heat. Every moment, its ancient surface is being altered. The Moon only looks frozen. It is actually participating in a continuous exchange with space. Even its extremely thin exosphere is not truly empty. Atoms of helium, neon, argon, sodium, and other species exist around the Moon in tiny quantities. Micrometeorites strike the surface. Particles are ejected. Solar wind delivers new material. Some particles escape. Others settle again. The surface is constantly being rearranged at microscopic scales. And this brings us back to the water, because the lunar water story may be much more complicated than simply finding ice in a crater. Scientists now know that water exists in permanently shadowed regions, but water has also been detected on sunlit terrain. And evidence suggests that water on the Moon can interact with the solar wind and migrate across the surface. So imagine the Moon's surface as a gigantic chemical landscape. Sunlight strikes one region. Solar wind arrives. A hydrogen atom encounters oxygen bound in lunar minerals. A water molecule forms. Later, energy from sunlight or an impact can release it. The molecule moves. Perhaps it encounters a colder region. Perhaps it becomes trapped. Perhaps it eventually reaches a permanently shadowed crater. There, temperatures can remain extraordinarily low. The molecule may stay for a very long time, perhaps much longer than human civilization has existed. And this is why polar ice is scientifically precious, not because ice itself is mysterious, but because ice can preserve history. A layer of frozen material can contain chemical information about the environment in which it formed. If we can determine when different deposits formed and where their material came from, the Moon's polar regions could become a record of how water and other volatiles moved through the inner solar system. NASA's Lunar Reconnaissance Orbiter has found evidence that ice deposits are more widespread than previously thought, including permanently shadowed regions beyond the immediate South Polar area. But even now, there is an important scientific caution. We should not imagine a giant underground lake beneath the Moon. The evidence does not support that simple picture. Much of the known lunar water is thought to exist as ice in cold traps or as molecules associated with lunar soil. The exact distribution, depth, purity, and history of these deposits are still being investigated. And that uncertainty is actually exciting, because the next missions can test it. A rover could travel into a permanently shadowed region, a drill could penetrate the soil, an instrument could analyze the material layer by layer, and suddenly something that has only existed as a remote measurement becomes a physical sample. A scientist could hold a piece of the Moon containing water that may have been trapped there for an enormous amount of time. That would be more than an engineering achievement. It would be a new page in the lunar record. And future missions are designed around precisely this kind of investigation. NASA's lunar science priorities include studying the Moon's magnetic history, its interior, its water and volatiles, and the processes that shaped its evolution. Seismometers, magnetometers, and electromagnetic instruments are expected to provide much more detailed information about what lies below the surface. The important word is below, because despite everything we have learned, we have barely touched the Moon. Humans have walked on only a tiny number of locations. Robotic spacecraft have photographed enormous portions of the surface, but photographs are not excavations. Gravity maps reveal hidden structures, seismic waves reveal internal boundaries, spectrometers reveal chemistry, magnetometers reveal invisible fields, but direct samples from deep lunar material remain extremely limited. There may be entire geological environments beneath the surface that we have never directly examined. And that is why the title of our journey becomes more meaningful. What is hiding beneath the Moon? Perhaps there is no single answer. There is the crust, beneath it the mantle, inside that the metallic core. But beneath the physical layers is another kind of hidden structure: time. Billions of years of it. Every layer contains a different chapter. The crust remembers the magma ocean. The volcanic plains remember internal melting. The magnetic minerals remember an ancient dynamo. The impact basins remember collisions. The gravity field remembers buried structures. The faults remember cooling and contraction. The polar ice may remember material delivered from space. And the Moon's orbit remembers its gravitational relationship with Earth. The entire object is a record written in rock, written in gravity, written in magnetism, written in scars, written in ice. And perhaps this is why the Moon has remained so fascinating for thousands of years. Ancient people looked at it and saw a bright object crossing the night. Astronomers later saw mountains and craters. Apollo astronauts saw a landscape. Modern spacecraft see chemistry, gravity, magnetism, and ice. And future explorers may see something deeper still. The Moon keeps revealing another layer whenever our instruments become sensitive enough to look. That may be the most important lesson. The universe does not necessarily hide its secrets because they are far away. Sometimes they are hidden because we have not yet learned how to see them. For centuries, the Moon's dark regions were imagined as seas. Then telescopes showed mountains. Spacecraft showed craters. Seismometers showed an interior. Gravity measurements showed buried structures. Spectrometers revealed water. Magnetometers revealed ancient magnetic fields. Each new instrument changed the moon. Not physically. Our understanding of it changed. And perhaps the next transformation will come from the lunar poles, or from a new seismic network, or from a sample returned from the far side, or from a piece of rock excavated from deep beneath an ancient basin. We cannot know which measurement will change the story, but that is what makes exploration worthwhile. There is still room for surprise. And perhaps one day, a spacecraft will land near the South Pole Aitken Basin. It will look across a landscape that formed billions of years ago. Below its wheels will be layers of ancient material. Far beneath those layers will be the mantle, deeper still, the metallic core. And somewhere beneath that enormous landscape may lie the remnants of processes that began when the moon itself was being born. The spacecraft will send its measurements back to Earth. Numbers, images, spectra, seismic waves, tiny variations in gravity, and scientists will begin comparing them with everything we already know. Maybe one of those measurements will finally explain the strange mass beneath the South Pole Aitken Basin. Maybe another will reveal a new detail about the core. Maybe a sample will clarify the moon's magnetic history. Maybe the polar ice will reveal a chronology of water arriving from space. Or perhaps something completely unexpected will appear. That has happened before. And if there is one thing the moon has taught us, it is this. Never assume a familiar world is a simple one. We have looked at the moon for thousands of years. It has been in our sky almost every night. We have mapped it, photographed it, walked on it, and still, we do not fully know what is beneath it. Perhaps that is the strangest thing of all. The moon is only about a quarter of Earth's diameter. It is our closest major celestial neighbor. It is so familiar that children learn its shape before they understand what a planet is. And yet inside that familiar sphere is a history stretching back more than 4 billion years. A history of molten rock, violent impacts, ancient volcanoes, moving metal, magnetic fields, cooling, contraction, moonquakes, water, and a gravitational relationship with Earth that continues to this day. So the next time you see the moon, look at it differently. The bright surface you see is only the outermost page. The craters are not simply holes, they are timestamps. The dark plains are not oceans, they are frozen remnants of ancient volcanic activity. The bright highlands are not untouched, they are pieces of an ancient crust. The poles are not simply cold places, they may contain trapped volatiles and records of the solar system. And the center is not simply a ball of metal, it is part of the story of how the moon once became magnetically alive. The moon is not empty beneath the surface, it is layered with history. And perhaps the deepest mystery is not what is hiding beneath the moon, but how much of that history is still waiting for us to discover. Because we have only begun to look. And if you enjoyed traveling beneath the moon with me tonight, consider subscribing to The Wandering Neuron. There are many more mysteries waiting beyond the surface, and I would love to explore them with you. Thank you for being here, and thank you for wondering. Good night.